All right. Okay. So let's go back to our limiter business and see what we can do on that. So let me clear the command window and open our burgers DDT again. So that's what we are left over from our last class. Okay, so now let's just walk through a little bit the progression of the development of this code. So in the beginning, we were doing no reconstruction. So the UL is exactly equal to the U at the left, and UR is exactly equal to the U on the right. Okay, and we have been using a central average scheme which doesn't work, and we progress to upwinding scheme which works for most cases, and we advance to Goodenough scheme which always give you physical solutions. And then we are not satisfied with first order scheme, so we went back to the reconstruction of UL and UR, and we did a fancy extrapolation reconstruction. That gives us second order accuracy but creates non-physical oscillations. And today what we're going to do is we are going to improve on this part. We are going to keep the flux reconstruction to be exactly the same. We are very happy with Goodenough scheme for any scalar conservation laws. For vector conservation laws, we can do the numerical dissipation way. That is actually easier than a Goodenough scheme, right? But we are going to keep this as the same and work on the reconstruction. Okay, so the first thing we need to do in the reconstruction is to compute the R, right? We need to recompute the R. So when I'm computing UL at I, okay, so UL at I is what? This is because UI plus this. Okay, so UL of I is the interface at I plus half, right? Is immediately to the left of the interface at I plus half. So my R should be U of I plus 2, right? Minus U of I plus 1 divided by U of I plus 1 minus UI. Is that right? Right. Okay. And for example, let's say let's use the mean-mode limiter for now. So if R is greater than 0 or less or equal to 0, okay, what should phi be? 0. Okay, and else if R is less than 1, phi is equal to R, and else R is equal to 1. Right? Do we know if
it should be phi equal to 1?
Oh, phi equal to 1, yeah. And let me just test something, because when I'm doing the division, there is a good chance I'm going to get infinity or 0, right? So if I have R equal to 0 divided by 0, R is a nan. Let me test the case. If this is actually false. So okay, so in the case of nan, I'm going to get phi equal to 1. And what if I have R equal to 1 divided by 0, infinity, and R is less or equal to 0, false, R less than 1, false. Okay, so when I get infinity, phi is equal to 1. I'm happy with both cases. All right? All right, okay. And I mean, things that, like when you are performing a division, it's you need to be very careful, because that's a place where you can get zeros. I mean, you can get infinities or nans. And you want to make sure during the if statements, the choice is something you're happy with. Okay. Okay. Then what I have is this is equal to this times phi. All right. And in fact, I'm going to code this up. I'm going to cut this and just call this as a function, right? And the function phi is equal to limiter r. Okay, I'm going to do that. So instead of saying phi, I'm going to say a limiter. All right. So I can reuse what I'm doing later on. Okay. So here another. I need to go. But like here you can do the same thing. R in this case, because I'm extrapolating towards the left, I need to do u of I plus 1 minus u of I divided by u of minus 2 minus u of I plus 1. It's symmetric. Right now we are looking from the right to the left. And this again is multiplied by limiter of R. Okay, so I think we get to go, but just maybe we have a chance to run the code. And hopefully it works. Nope. You got a class going on afterwards. Okay, so maybe we'll test run that next lecture. All right. Okay, cool. So I'll see you next Monday.